I'm Dr. Olga Ras, and today I would like to guide you through our newly updated Optica Market Intelligence Library. Market Intelligence Library is a one-stop resource for reliable market reports focused on photonics, reports that normally cost thousands of euros. But as an active Optica corporate member, you get access to them as a part of your member benefits at no extra cost. So use it, and I'll show you how that works. We go online and we land on our main landing page, optica.org. From there, we can immediately move to the relevant tab of Industry Resources, and from there, right away to Market Intelligence Library. Here, you can see the entire collection of our focused market reports. You can filter if you like. Scroll down, take a look at the reports, choose the report that interests you, put your business email address, and in one click, the link will end up in your inbox. Go to the email and just click the download link. And here is the result. You can immediately view the PDF of the market report. That's all it takes. The Optica Corporate Intelligence Library saves your team time and money. It ensures you always have the latest commercial insights you need. So when you're working on preparing a strategy review, a business case, a customer or investor pitch, connect, explore, and download the latest data. Thank you for joining me, and remember, our corporate engagement team is always here to help.
The space sector is changing fast. Data demands are exploding, security is critical, and sustainability is at the core. On Tuesday, September 23rd at 10 a.m. Eastern, 4 p.m. in Central Europe, join the Optica Online industry meeting discussing photonics for NewSpace. We'll explore how optics and photonics are making satellites smaller, lighter, more power efficient, and faster to deploy. Topics will include space optical links beyond 100 gigabit per second, integrated photonic packaging for harsh environments, miniaturized optical payloads, which will include compact telescopes, beam steering solutions, and much more. Who's joining us, you wonder? ESA, the European Space Agency, NASA, Safran, and many technology suppliers including Embryonics, IMEC, Epiphany Design, Microlam, ANSYS, BPI, and then Confocal. This 90-minute event is free to attend thanks to the growing number of sponsors supporting Optica's work. That includes PIX, BPI, Wancient, Vanguard Automation, Micronic, IMEC, and ANSYS. So let's get started.
Hello everyone, the day has arrived. Finally, we have the Optica Online Industry Meeting on NewSpace Technologies. I'm extremely happy to have today presence from Safran, from the European Space Agency, having one of the key companies in the ecosystem, Embryonics, here, talking about free space optical links, talking about the new demands for high reliability of photonic solutions, miniaturization, reduce of payloads. The next 90 minutes of your time are definitely worth it. I would like to acknowledge the huge effort of the Optica corporate members, and in particular our sponsors today. I would like to once again thank them, because this meeting and all the work that the team has done over so many days is free for all of you thanks to the support of BPI Photonics. Thank you for bringing your software here. Fix, thank you for bringing your packaging technologies. Quancient, your cloud-based simulations. Vanguard Automation, really great to have you here. IMEC, thank you for your constant support. And of course, the software simulations and the software design tools of ANSYS as a global platform. It is great to have you. Today, This is how it works. We always have two teams of companies. On one hand, we have the integrators, the companies who come here with a shopping list asking us what they want from the photonic industry, and then the enablers. And that's a list of everyone in the meeting today. Everyone in the Zoom room is an enabler. But I would like to highlight the ones that contacted us beforehand and asked to show one slide. And those are IMEC, Epiphany, Dencon, ANSYS, and VPI. Over the next 90 minutes, our job is to make sure that we connect those integrators with everyone in the room that can satisfy their demands. This is how it works, and we had organized many of these meetings. This is the calendar for upcoming events. On the 14th of October, we have the Photonic-enabled AI online meeting. Write down the date on 28th of October. Optica, augmented and virtual reality meeting, AR VR. That's gonna be spectacular. I also would like to remind that we have lots of face-to-face meetings, but in the 21st and 22nd of October, we are meeting in Sunnyvale to talk about photonic-enabled cloud computing with more than 300 attendees from the world, and especially from the Silicon Valley key companies in the industry. But today is all about space, and this meeting is organized for and by the corporate members. We have a growing list of companies whose job is to make sure that they come here and they connect with other companies. For them, we offer market reports, as you saw already in the preview, discounts, promotion, in general engagement opportunities. Thank you to all our corporate members for your constant support. And also, I would like to remind everyone that we have our biggest list of market reports from our industry. Go to optica.org/market reports, download all of them if you're a corporate member, because they are all free for you. I also would like to remind everyone that this meeting is live streaming in YouTube, so let me say hello to the YouTubers in the world. So hello YouTubers in the world. If you have any question, you can write in the chat and I will read it in the room. And this is of course also valid for the people here with me in the Zoom room. If you have any question during the meeting, you can write it in the chat and we will give you the voice so you can voice that question live. But most important, during the meeting, keep your camera on. This meeting is live, and the whole idea is this is not a webinar. If you came here to just listen, you can go to YouTube. This is here a meeting for you to participate and find out how you can answer the questions of the key integrators. And to start, Olga Ras, congratulations on you have achieved bringing the key companies in our ecosystem today. To start, let's go to Noordwijk, the Netherlands. Let's go to the European Space Agency and ask them what is NewSpace and how we can, as a photonic industry, enable it to them. European Space Agency, from Mission Control here, Harald Hauschild. Thank you very much for bringing today the technology of ESA, the floor, and the attention of everyone. We are global today. Is yours.
Thank you very much, Jose, for the invite and the chances here to reach out to so many people. Let me try to present. I hope that is working. Just a second, it's always the same. Okay, I think the presentation is okay now.
Yes.
And thanks for inviting me to talk about what we do at the European Space Agency in the field of optical and quantum communication. My name is Dr. Harald Hauschild. I'm in charge for the strategic program line that we have set up to deal with optical and quantum communication in a strategic line in order to support industry in a large and wide range, from big satellite integrators down to SMEs, startups, in the traditional way, but also in the NewSpace way, trying to help and motivate and boost the ecosystem in that field. Let me try to motivate a bit why we are doing it, why optical from space. Of course, some of you and certainly the speakers here are already knowing that, but just to underline what is so special on optical and photonics in space. We are used to an infrastructure on the terrestrial side to dial in every time with all data rates that we require, but we see this is not so reliable anymore due to some global exchanges around the world. But we are at the same time depending very much on the global networking around the world for different purposes. We need, this is the reason why we are here, an optical network in space in order to have global interconnectivity secured that we have resilience data network and can control where the data goes, with whom we are communicating. And of course, being a space agency, we also want to ensure that we extend that to space assets, to satellites, and also to the deeper space. Going to the moon is one of the stops that we want to add in that as well. Let me motivate with a little video, and I hope that is working, the thinking behind and what we are trying to do, and then I will guide you step by step to what we can do together potentially. I hope the sound was also working, but I think the video came across and showed what we are trying to do. We want to interconnect space and ground, want to interconnect the different nations around the globe with data networks that is capable and on the same level like we have on the terrestrial side. For this kind of networking, we need quite a number of technologies. We need lasers, we need photonic elements, we need ground station optical terminals, and you name it, in order to have this kind of demonstrations of the seamless connectivity with space and ground. So what we are looking for is a seamless integration of both, integrating space to ground, but also ground to space, in order to demonstrate that the networks are capable of routing the data wherever it is needed. For optical communication from space, this is especially important because, as you know, sometimes we have clouds in between the satellite and the ground, or the other way around, and we need to find a way to overcome this kind of cloud coverage problem that we have. The answer to that, and that is how we are trying to address it, is with a network in orbit. And so the overall chance that we see with optical is to build a network in space that is demonstrating and in the end implementing data rates of 100 gigabits and beyond in the longer term. We are currently implementing a project called Hydron, where we are demonstrating the interconnection of 10 satellites with 40 laser terminals around in space in LEO orbit. We do that together with a private investor, Kepler Communication, and a consortium of industries supporting the idea and the vision of ESA to have these kind of data rates deployed in orbit. And we are doing, with the second element of the program, an extension to other orbits. We do that as a partnership with Thales Alenia Space in Italy and with partners around in Europe to deploy this kind of extension to other orbits in GEO, in MEO, but you will see also to other orbits. Why is it important for the NewSpace? While we have players already, the important is that this system in orbit can not only do demonstrations and create future businesses for the companies involved, but it can also be used as a test lab in space. And that is why we are also very much interested in a call, and I will come to that in a second. This could be a call of interest for you in the future to have your own terminals deployed and integrated to this kind of very unique networks that we are deploying in space. Not only in space, we use the same program also to build towards new users, new services, to UAVs, to hubs, airborne in general, should be connected to this kind of data networks. We are looking for implementations on the maritime area, and in general, we are looking for providers of ground stations that can be deployed everywhere around the globe in order to connect ground with space. As I said, it is not only the laser links that is of importance, it is everything around, including the network architecture, the routing of the data, and the integration to existing fiber networks as well. This is also here size-wise not what we are aiming for only. We also want to go beyond Earth, being a space agency, and sharing with some other space agency the idea to go to the moon and go to Mars in human flight missions. We are also looking to extend this kind of network around the Earth to the deep space in order to lay the foundation for a solar system internet, as we call it here. Optical will play a large role because also here the demand for high data rate is extremely important. How can you participate and benefit from what we are doing together with our member states? On the optical fields, the most prominent part, I would say, is the Hydron program, where we are looking to the so-called Element 3 and the Evolutions program to new suppliers that test out their own technologies, validate their terminals, or validate part of the technology that you have developed. Here, this is something we can try to elaborate with you, how your product, how your idea can fit to it, and I come to some other elements in a minute. As I said, the range of developments are quite open. It has to do with optical communication. That is the main discriminator, I would say. And from there, we can, together with you, explore how optical communication can be used. Talk to us on that, and you will see there will be a way to accommodate your dreams as well. It's not only on optical communication, we also work in the same strategic program line on quantum communication, and also here photonics, lasers will play an essential role, especially for the space part as well. And we are coordinating our space strategy together with our member states in their national quantum strategies, and we see them deployed around in Europe quite intensively, also with quite some high funds around that. Some of them concentrating on quantum computers, but also increasingly more on optical and quantum comms. We are supporting satellites for quantum key distributions for both for the commercial and institutional use. We are working closely together with the European Commission on their idea of a European quantum infrastructure, EuroQCI, that we are building together with them. At the same time, we are preparing already for the future. While we are still on the journey for the first part, we are looking into the future of the quantum information network, where we are looking for quantum entanglement networks and all the technology that is required around that. And we see already some of these networks for demonstration purposes emerging around the world in different nations in Europe, but also way beyond. This includes the integration for experimental links with banks, data centers, critical infrastructures especially, and institutions. We do that also to motivate the idea, mainly because we believe satellites are necessary to have the global connectivity, to increase the distance between the placeholders, as the current terrestrial networks still have a limitation here of about 80 to 100 kilometer distance and about 200 kilometers in the fiber length. And as long as we don't have a quantum repeater that we can plug in and extend the networks as we do today with other kind of signals, as long as we don't have that, we believe the satellites will play a larger role for Europe. But if we go intercontinental, if you go globally, the satellites are there to increase the distance of these kind of networks. And this is true for both for quantum key distribution systems, but especially also for entanglement distribution networks. And we are currently preparing a mission called Quasar that should look into a European demonstrator of this kind of technology. Nearly the last slide, also to underline for what is the program good for you. The program, as I mentioned, is a strategic program line for optical and quantum communications. The short name for that is Skylight. And the idea is here to grow the ecosystem around in Europe, to help the companies to come with their own ideas, having their own roadmap on the technology discussed, and have this idea and this dream funded depending on the technology readiness level between 50 and 80% funded. And this we do in cooperation with our member states. On the other side, we are also preparing the overall roadmap for the technology, areas that we believe are important to be tackled. And we are publishing this on a yearly work plan, which comes then with 100% funded activities that we propose, where you can hand in your proposal in coordination for both areas with your national delegation, which will then give the authorization for the funding on that, on this activity. The main mission here is that we are trying to place the know-how transfer from the laboratory, especially on the quantum fields, into the factory to connect the academia with the industrial players around in Europe. Final slide, an invite to you to meet the ecosystem that we are building up slowly. We just had our annual Skylight conference in Dublin, and some of you have potentially participated to that. We are now counting around 300 participants, and with that is becoming one of the largest optical and quantum communication conferences in Europe. All the players around Europe is there. It is to interconnect you with different players. Here you can present what you have done in pitches and make the community know what you are working on and how you want to collaborate. The next one will be in June next year. The location is already selected. It's Tenerife, where also our optical ground station is placed. The exact date you will see on the ESA web pages very soon. And with that, I would close my presentation. Thank you for your time listening to what we do in ESA, and please don't hesitate to come to us if you have any questions and proposals. Jose, back to you.
Thank you, Harold. So you are here in the meeting of the of the enablers and technical enablers. So if you can think of the really 3 bottlenecks or really hard challenges to challenge this community, like which 3 doesn't let you sleep well at night?
That's a very good question. For me, the most important thing is the number of suppliers in many areas. We need to have independence in Europe of this kind of technology. This technology is breaking for the future. It's super important to have multiple suppliers. It's also to grow the ecosystem so that we can see in which areas we should evolve. So for me, the ecosystem is one of them. The second is the chances to demonstrate the technology in orbit. That means we need to have players that are willing to go the challenge, and we are here to help them as well. So we want to grow the ecosystem from this perspective, keeping the know-how in Europe. And the third one is the transition between the optical and the quantum fields. We are trying hard since 20 years to master the optical technology, and I think we are doing well. Besides that, we need more suppliers and new ideas. But we now need to bridge over to the quantum fields, and especially the relatively long term that we have in front of us for quantum communication with entanglement networks. That makes me nervous. And we see around the world many players working on that, and we need to join our forces together around in Europe to make that happen here as well. And that is what ESA is there for.
Thank you, Harold. I believe that if you stay all over the next 90 minutes, I believe you will meet quite a few suppliers and potential providers for the services that you look, both in optical development, we're great about it, but also especially in quantum, which really grows up, and we have quite a few members active in this. Maybe if you could announce the calls that you for the projects that you believe are the most relevant are now active for the people in the group to apply.
The Skylight program, as we call it, has an open call procedure. So any time of the year you can come with your ideas with an outline proposal, and you will see on the website of ESA, if you look for Skylight open calls, you will see some guidance to what information we require in order to make a first evaluation of your ideas, to give you guidance on what we see is missing here, also to interconnect you to different stakeholders in that frame, which might make sense as well. And the good thing in that, and especially for newcomers, is that the IPRs, the intellectual property rights for this kind of call, belong to you. So you can extend them later on. This comes with a little caveat that we would like to see a bit of a co-investment from your side in order to see this is something of your strategy where you want to grow. And in the end, this is what also NewSpace is. There is a business behind that you want to somehow capture. On top, we have the, as I mentioned, the yearly work plan. Also here, it's worth browsing through. We have just finalized the work plan for 2026. We have discussed it with our member states and has been approved. It will be published relatively soon. And here we have this time 19 new projects around in optical and quantum communication that we think need to be tackled. This will be done in open competition. In many cases, we are placing multiple contracts for one activity, depending on the quality of the proposals. And then the third one, which is slightly attached to it, is a special call for Hydron Element 3. So everything that has to do with the direct connection that you would like to have with your perhaps a bit mature technology already to interconnect it to the networks that we are currently building up in space. This would be Hydron. But independent of that, just send me and my colleagues an email, and we will handle and guide you to the right calls.
Thank you, Harold. I think as I look through our participants, I see ID Quantique in the group, who is really a professional, let's say, and quite a young name, invested very much into the quantum technologies. Jeremy, are you with us?
I am with you, yes. Thank you for the name call.
Perfect. What's your impression? How can you address the call from Harold? Quantum technologies, quantum key distribution.
So ID Quantic, we are providers of QKD solutions, right? Quantum key distribution solutions end to end. Of course, not yet in space, but we're certainly present in the space field. We are also working with the Eagle One project, where we're generating QRNG, space-ready QRNG equipment. Large project, right? So that's a big step for us, going space-ready with our stuff. And on the optical ground station level, we are talking more about SNSPD systems, so detectors basically at any wavelengths you want, which are extremely sensitive. So either for tenuous light, either long distance or short distance, or super fast count, or specifically, we now have released polarization maintaining detectors, which allows you to use polarized QKD free space directly to our detectors. So we're very open to discussing that with you, Harald, and your teams, specifically for the ground stations.
Do you have any questions?
May answer directly, Olga. Yes, and we are in contact already. As you said, the Eagle One project is something you are participating in already. I did not mention many projects on purpose because normally the projects have already their participants, and then it's a bit difficult to get especially newcomers into that. But you are already settled here, and indeed, the quantum detectors will play an increasingly role on the ground segment itself, but also there are plans to have interconnections in space as well. So we need to bring these detectors also up in space.
Thank you, Harold. And I would like to, when we started to discuss already the designing the entire systems and going from orbits to orbits, I would like to bring to conversation really a professional in designing the systems in entire physicality of them, and this is ANSYS. Stephen, would you like to share your expertise and tell us how you are able to address Harold's requests?
Absolutely. Go ahead and share my screen with you guys. So what I'm most excited about with all of this is as we start getting away from exquisite systems and moving more into the proliferation of space, I see this as a really good opportunity for a lot of startups. I think there's going to be obviously still a place for groups like ESA and NASA, obviously, but I really see this as kind of like what Silicon Valley was in the 70s and 80s when it really was starting to kind of blow up and get a lot of startups really kind of getting involved with that. I'm starting to see that happening with space now as well, where it's really kind of lowering the barriers to entry. And I think part of that comes down to just the technology. We have the ability to not look at things like doing very expensive cold chamber tests and a lot of basically build and break type scenarios, but instead we can simulate a lot of those things. And that's kind of where our company comes into play. So an example I kind of threw together here was just, what if we were looking at, let's say, the damage to a satellite in space from another satellite? What would it take to model something like that and see the effects of it? Well, we'd have to start from the mission level. We'd have to look at the trajectories of those satellites. Where's the damaged satellite? Do we have a bird in the area that can actually see it, has the right equipment on board to view it? We finally find those pieces of the puzzle. Then we need to figure out, well, what's actually going to happen to the system itself? We think about like the orbital mechanics of this. This goes beyond just optical tools and things of that nature. We're looking at where that orbit is, where the plane of the ecliptic is, the solar loads on that item. All that's going to affect the temperatures here. What you're seeing in that little graph there is we just picked a very simple CubeSat to keep this a very cheap, inexpensive system. And it's got a primary and a secondary. Obviously, the secondary is smaller than the primary, so you see a bigger fluctuation in temperature than with the primary. But we can look at those effects. We can look at that thermal load. What does that do to the optics? What does that do to the mounts and put stresses on the optics? So you can look at how that's happening. What's actually happening to the mechanics? Is it twisting these things? Is it putting actual pressure on the system and stress on the optics? And then bring that into our optical system so we can actually see what is the distortion to our optical system. And then finally, what did that do to your optical system? Can you still see that bird? One on the left is the image of what we'd expect to see. One on the right is actually when we apply all of those optics to it. And this goes beyond just optics. Obviously, I chose an EOIR system here to kind of taking that to the sensor, but we could have done this with, say, telecom as well. If we're looking at optical communications, what kind of distortions happen there? And not just in space, but as we pass through the atmosphere, can we look at all of those fluid effects on the optics as well, the optical effects of fluids? So we start modeling all of those types of items, which traditionally would have been very expensive to test. And that's why I really see this as an exciting time for smaller startup companies. Start lowering that barrier of entry, make it more accessible. And I really am excited for this time because I think we're going to see some stuff that, maybe the big dogs didn't think about and really kind of get these items to the forefront. So very excited for what will come next.
Thank you, Steven. All right.
Sorry, Stephen, I need to ask this because we have had a lot of participation from ANSYS. You're a sponsor of the meeting today. It is the first time that you present ANSYS as a part of Synopsys. So we need to ask, how is that going? What is the current status? How do we introduce it to other members? Did anything change with this now being part of Synopsys?
I'm not sure how much of that I can really share necessarily and how much of it's out there in public yet. But yes, we are acquired by Synopsys. That happened this summer officially. They finally got approved by everybody. I'm actually very excited about it because we've been partnered with Synopsys for some time. They handle a lot of the chip elements. ANSYS handles a lot of the physics of things. So now we're able to literally go what we call chip to mission. So we can actually go from that level all the way up, which I'm very excited about. So I think we're going to see, just as we're starting to see, this explosion in NewSpace, I think we're going to see a whole new level of abilities between the merger of Synopsys and ANSYS. So I'm extremely excited about the opportunity. Where that leads, I don't know yet, to answer your question more directly.
We will see. And Stephen, are you also able to introduce, let's say, what type of the photonics components, or let's say even optical assemblies, are you able to simulate or introduce to the systems? Because quite often, all of the systems contain either deformable mirrors or active actuators to correct for the atmosphere disturbances. So how far are you in simulating all these different components?
Well, the nice thing is as Ansys kind of built itself up over the years, we acquired a lot of companies. So I came over from the ZMAX acquisition, for example, on the optic side, but we do have mechanical tools as well. So if you're looking at, say the movement of pistons, even if you wanted to look at, let's say, how that was actually moving, maybe it's actually on an actuator or something of that nature, we could actually look at like the electrical systems on that are creating that actuator and how that's then creating the mechanical motion for the deformation in the system. All of those can be modeled with various tools. So it's just a matter of what tools do you need to assemble? Do those tools all talk to each other fluidly? Really just kind of comes down to the problem itself. It's not going to be any one tool within the suite.
Thank you. Because didn't ask you just of the curiosity, because I was curious to know if you were already working or were planning to work with our next speaker, who is Demcon Focal, right? These are the guys that are able to develop any optical system. And I believe two of you are already talking, but if not, this is definitely a good introduction. And with this in mind, I would like to introduce our next speaker to the floor, who is Justed Ha from Demgon Fakal. Just, the floor and attention, everyone, is yours. Just, we don't hear you.
Hello? Yeah.
Yep.
Okay, great. Yeah, perfect. So thank you for the introduction. Good afternoon, everyone. For some, good morning. My name is Joost de Haan. I'm an optical engineer from Demcon Focal. It's a pleasure to speak to you today at the Optical NewSpace seminar. So for the people that don't know Demcon Focal is the optomechanical subcompetence group within the Demcon group. We are a leading Dutch technology developer and system supplier. We specialize in the design and realization of advanced optomechatronic systems and modules for high-tech industries, including the rapidly evolving new space sector. All our multidisciplinary teams combine expertise in optics, mechanics, electronics, and software, enabling to tackle complex engineering challenges from concept to production. Our projects are highly diverse, ranging from small-scale feasibility studies. For example, if a customer comes by and they just want to have a small feasibility study done, that is also possible. But it can also be that you can go up to a whole complete machine building project that is actually fully engineered and integrated for deployment. This flexibility allows us to support customers at every stage of the innovation journey, whether they need a quick proof of concept or a turnkey solution. With a lot of experience in precision engineering and a proven track record in aerospace and semicon and in scientific instrumentation, Demcon Focal has become a trusted partner for both established industry leaders and innovative startups. Our approach is characterized by those close collaboration with our clients and a deep understanding of application requirements, including of those required for space qualification. A prime example of our capabilities is the Fine Steering Mirror, or FSM, developed in partnership with TNO, the Netherlands Organization for Applied Scientific Research. This collaboration combines TNO's expertise in optical system design and space qualification with Demcon's focal strength in precision engineering, system integration, and industrialization. The result is a compact, high-bandwidth mirror system that enables dynamic beam control for demanding missions. The FSM is designed to meet the stringent requirements of modern satellite platforms, where size, weight, power, and reliability are the most critical factors. So let's take a closer look at the Fine Steering Mirror key specifications. Its readiness for operational deployment. The FSM offers a tip tilt range of plus or minus 2 milliradians and enabling precise beam steering, essential for maintaining stable optical links between satellites and ground stations. With a bandwidth greater than 1 kilohertz, the system can rapidly correct platform jitter and other disturbances in real time. Its angular resolution is better than 2 microradians, supporting the high precision pointing and tracking required for advanced optical communication and sensing. Despite the performance, the FSM is highly energy efficient, consuming just 0.2 watts at full stroke, making it ideal for power-limited small satellite platforms. Importantly, the FSM has reached technology readiness level 8, meaning it has been demonstrated in orbit and is ready for operational deployment. This technology is already being integrated into optical communication terminals, Earth observation payloads, and even quantum key distribution systems. With its compact, lightweight, and robust design, the FSM is already supported the next generation of agile and high-performance NewSpace missions. In summary, DEMCON-Focal's fine-steering mirror demonstrates how close collaboration, technical innovation, and commitment to quality can deliver robust solutions for the most demanding challenges in space. We are proud to contribute to the advancement of agile optical communication and high-precision pointing technologies, supporting the ambitions of global space community. Thanks for your attention, and I look forward to your questions. Thank you.
Thank you. Have you already applied for some of the SS projects?
Yeah, we are actually also working on Eagle One. So we are designing the wavefront sensor on Eagle One. Yeah, so that's also a project, and also one of the big projects that we work on are we've designed the optical and optomechanical system for the laser guide stars of the extremely large telescope of ESO. And that's just a couple examples of larger projects that we work on. We also, because photonics is almost in every sector, it can be applicable to the agri-food culture sector or also medical. So it's not only space for us, it's also a bit wider than that. But yeah.
Perfect. So it looks like it's an eagle party here.
Yeah, it
Meanwhile,
almost looks like it.
meanwhile, we have a question from iMac. So
Yes.
please unmute yourself and ask.
Yes, Joost, I had a question. So you said you're also using it for Earth observation. Can you a little bit more go in more detail? What type of missions are you using it? Why and how you do it?
Okay, to be fair, we are closely working together with a company is called FSO that is also in DEMCON in the DEMCON group, and DEMCON Focal is the design house of FSO. So they are actually they integrate the FSM in their systems. And one of those is also in a Earth observation system. And we also have run any other some projects here for other companies, but I cannot go too much in depth for this. So, but they are in some systems for Earth observation. Yeah.
Bavo, are you happy with an answer? What was the reason you asked?
Just
Yeah.
out of curiosity, I have some background in Earth observation from my previous job, and I just want to understand a little bit more. Meaning, what kind of mission is it for a high resolution Earth observation mission, or is it for something
Again,
else?
I have to ask them because at this moment I don't know for sure. But we can come in contact later on maybe.
Yeah, would be nice.
Yeah.
Thank you.
Yeah, cool.
Perfect. Just, I have actually a question because you mentioned that you also use the system for the QKD, but I know that for the let's say my novice knowledge tells me that usually you need a much higher aperture for the mirror to be compatible with the really quantum, because right, there every photon counts and you need only one, and so the bigger the aperture, the better. And your mirror seems to be only 18 millimeters. How do you deal with the very low signals?
True. We are actually now are in a development track together with FSO to design a larger FSM. This is already in production. So this is, but the FSM that you've seen I've shown that one was actually demonstrated in space. So and the LS so the larger is not in space yet. So it's harder to actually back that up still. Yeah.
Okay, you're on the way.
Yeah.
And I'm
Yes.
asking because I might have a perfect partner or customer for you for the future. And this is David Mackey from Embryonics. David, you're welcome to the floor to share your advances, what you're searching for, and what you can offer yourself to, for instance, ESA.
Thank you very much, Olga, and also thank you, Jose, for the invitation. Greatly looking forward to speaking. This is loading. Hopefully you can see my screen. So Embryonics, we are a satellite telecommunication hardware company, in particular for optical transport networks in space. So I'll try and describe that in a bit more details. We are headquartered in the west coast of Ireland, a place called Galway. And we were thrilled to host Harold and the Skylight conference this year in conjunction with the Irish government in Dublin. It was a very successful conference, and highly recommend everybody go to Tenerife next year. It's a great conference. And also thank you, Harold, and Isa has been a great collaborator and supporter of Embryonics in developing our core technology over the last 10 years. So we formed the company 11 years ago, after also about a 10-year research period as part of a local research group here in Galway called the Applied Optics Group in the National University of Ireland, Galway, where we specialized in adaptive optics systems for free space optical communication through the atmosphere. But we've been working on the end-to-end optical transport network technologies for full satellite optical networking for the last, as I said, 11 years to commercialize them. As this has covered both optical terminals, transceivers, and lots of other optical systems, which I'll describe in this. So we recently passed 100 employees, probably about a month ago, and we're hiring actually a lot more in the next few years. So we're going to be about 225 people in the next 2 years. So if anybody is looking to join the space industry and has experience in either photonics, optics, mechanical engineering, manufacturing, packaging, we are hiring all those positions and really looking for talented people who want to work in this cutting edge technology. And in terms of our other core partners that we've worked with to develop our core technologies, Space Systems Command in the US, DARPA has also been a key partner, and then more recently the European Innovation Council, who are co-funders in Embryonics. And in terms of building on some of Harold's just points for the satellite optical networking, so we are proudly also part of the Hydron program, which is again a fantastic program that's really addressing some of the core challenges of really beyond just point-to-point optical communications, but really the whole end-to-end optical transport and networking of these satellites in space, which is really not a non-trivial problem, as we said. So essentially, look, a terrestrial fiber network is common enough for mobile phone networks, but essentially in space we have a mobile phone network. So if you're trying to imagine a fiber optic network that's constantly changing its topology, this is really the challenge that we're trying to solve with these satellite optical networks. There has been obviously a lot of recent announcements of spectral considerations, and really where the mobile phone network will become more supported by these satellite optical transport networks. So what they're going to be referred to as these non-terrestrial mobile networks, where really you'll have direct-to-device, so direct-to-your mobile phone communication will become more prevalent in these next-generation devices. This is really adopting this dedicated mobile satellite spectrum that will allow direct-to-device. But then there are other options where there's previously the ones that have been rolled out have been more looking at this selected shared spectrum with the mobile network operators. But this dedicated spectrum will now offer complete independence also from mobile network operators. So it's an interesting time for the whole satellite optical transport network that's going to have to try and support these mobile network systems going forward in a much more dynamic way. So the more traditional sort of satellite communication would be just radio type systems like these you'd see on either ships or more SpaceX type satellite dishes that you'd see maybe to homes and things like this. But as I say, look, it'll get more and more direct to your device in the future. And in terms of what is also quite a challenge for these satellite optical networks is they are currently all very much independent. So even though there are multiple satellite optical systems up there, they're all not interoperable. So we are very fortunate to be part of this DARPA Space Bacon program, which is to address this issue, similar to the Hydron program, where we're trying to get a unified standard. But this DARPA program was to address that there wasn't a standard at the time, and to try and make an optical terminal that could be interoperable between all these different satellite networks, be it a government system, SpaceX, Amazon Kuiper, Telesat Lightspeed, or any other of the operators out there. And so look, we were down selected as the prime contractor to make the optical front end, and then we're working in conjunction with Intel Altera, who are developing then a reconfigurable optical photonic modem that can support both coherent and direct detection type communication formats, things like on-off keying, pulse position modulation, and then the higher order QSFR, quadrature phase shift keying type coherent modulation formats. In terms of then how we are solving this in embryonics, this sort of end-to-end optical communication systems. So as I said, look, it's a number of different technologies in the technology stack. From the most visible one that people are familiar with is these optical terminals. This is literally the optical telescope. So this allows to expand the beams. You'd have an FSM in that, similar to what DEMCOM we're making inside one of these systems that allow you to point the laser beam very precisely. But we also then have what we would call a coarse pointing assembly that points the overall larger beam telescope system. What's unique about embryonics, STARCOM, as I said, look, it's interoperable both from a pointing acquisition and tracking perspective with all the other standards out there and other constellations, but it's also got this very large aperture freeform telescope with 124 millimeters, which enables these very long-range links with higher data rates. So obviously, the larger your aperture, the more laser power and photons you can receive with less laser power, I should say. In terms of the other core systems, so we also develop these optical amplifiers that are multi-waveform compatible. A photonic modem that we are, so I can now announce also today, as of today, that we are also developing a radiation-hardened and coherent QSFP module. That'll be beyond 100 gigabits per second, and that's targeting radiation environments all the way up to GEO and MEO, which is sort of a critical technology for these future really high throughput optical networks for these other orbits. And then last but not least, we also do these optical ground station systems that are based on adaptive optics, which is the key part for getting really high throughput from the ground to space, is this adaptive optics system that solves the atmospheric channel problem. And I'll briefly talk about Terabix at the end. While not the Eagle mission, we are part of a QKD mission, which we're very proudly doing with Spectral, who are a Singaporean company that specializes in generating quantum key signals. And then we are also, the other satellite provider is KNA Kongsberg and Nano Avionics, who are doing the CubeSat demonstration module. Embryonics are developing the optical head that is compatible with then this QKD payload from Spectral, which look, some of the people on the call are also involved in this mission, which is very good. As I said, look, I'll briefly touch on this product, which again has been developed with the European Space Agency. This is what we call Terabix. It's for very low power but high throughput photonic interconnects for digital communication within satellites. So while optical networking of satellites is also important is the networking within the satellite. Where this is becoming quite prevalent is from either central processing unit to another central processing. So think of multiple FPGAs talking to each other within a satellite for multiple redundancy of FPGAs, or it's just large processing that's distributed across multiple CPUs. But the other key application going forward, this is again for this direct-to-device type applications where they're making very large radio antenna and have to send digital signals to these very large digital beamforming arrays, and this photonic interconnect really enables these sort of very large flat panel type radio antenna. So look, there's lots of different areas where photonics and optics can be applied to space. I'm highlighting a few just because I think it is worth for other people on the call to be maybe aware of where the market is and also where things are progressing. So obviously optical intersatellite links are really advancing from beyond direct detection to coherent links is really where the market is going. Optical switches is a core technology that I would suggest if anyone's in the optical switching market, they should really start investigating space as an actual market application. Again, contact Harold about the Hydron program. It's definitely a core technology that will be more and more adopted for these networks in future. Optical amplifiers, again, very high power optical amplifiers. There's a continuous need for higher and higher power for these very high throughput type systems. As I was mentioning, there's a lot of photonic interconnects within the satellites for central processing and these digital beamforming applications. But additionally, then there's also worth talking about analog RF photonics, which is to try and replace these typically larger analog and electrical RF sort of copper cabling. So there's a real need for very broadband type radio frequency applications, which photonics can address quite well. But there's real technology challenges to develop these technologies. So I highly encourage people within the industry to really address those. And thank you.
Thank you very much, David. Thank you for a great presentation. Embryonics is also featured at the Global Photonics Economic Forum in Malaga in 15 days. You are doing You're an example to follow when it comes to collaboration and cooperation. As you said, there are many people in the room who are partnering with you. I just look around. We have Jeroen Daus from Fix. We have Jennifer Lee from Biosystems. And what are the main challenges, the main room for collaboration? What is your shopping list? What do you want from the photonics industry?
Very good question. So again, I would echo Harold's thing. Diversity of supply chain is a key thing. Look, we tend to have only one or two suppliers we can approach for some of these very niche space applications. So having a wider and more robust supply chain is highly encouraged. So really, I would encourage anyone who's in the photonics industry. The space market is becoming much larger than maybe you're aware, and it's not just no longer a niche play. So I would highly encourage everybody to start really
David,
applying their technologies and seeing if there's a market fit. Yeah.
David, you and I are friends for many years. I think I can go a bit further than we have a resilient supply chain. Let's talk about the laser. Let's talk about the laser. I guess that you are vertically integrated, but you integrate an external laser, right? Could you specify it a bit more? Yes. Are there any unmet needs there?
Yes, so we are, so for this QSFP module we're currently developing it. So what's unusual for a QSFP DD module is this has to be a dual laser source system. So it's quite a compact laser sources work really challenging form factor to hit. So you have to both transmit and receive lasers as well as the local oscillator. So this is core technology that we're looking for, wider market adoption that we're looking for good suppliers on. So we've been contacting every laser supplier in Europe to really try and source this one. So if anyone has a good solution out there, we are eager to hear from you.
We have a few people in the room who want to talk to you, and the first one is Jeremy Dubois from IDQ. Jeremy, what's on your mind?
Well, I was questioning actually super interesting because you're talking about OGS. A lot of people are talking about spacecom and satellite to satellite, but few people are as vertically integrated as you are, I think. And more interesting to us is that your optical ground stations are operating at 1550 nanometers. So I was kind of interested in, you mentioned QKD. Is this something that you're looking at, and what kind of challenges are you actually facing right now?
So yes, so we have this joint QKD mission with Spectral, and so that's not in 1550. So again, I will let Spectral talk about the wavelengths they use for their QKD mission, but it's obviously much lower. In terms of the challenges with that, again, it is getting good laser sources that are high power for those types of applications. There's many challenges with that, particularly on the ground station side. There's not many suppliers that would be, so they're Spectral, for instance, they're partnering with a number of different partners for the optical ground station part across the globe, and they are looking for more and more partners on that mission. And say ID Quantique probably, are you familiar with Spectral? I'm sure they would love to know you as well.
You'd have to write it down in the chat. Sorry, I just couldn't catch it so precisely.
That's okay. I shall message you. Thank you.
Jeremy, congratulations on everything that you're achieving in the field of QKD. So you guys are fantastic. David, you talk about the laser. So let's start making connections here. One of the companies that really wants to talk to you and wants to do business with you is the company Epiphany. I am really happy to have here one of the founders of Epiphany, a good friend of mine, Jorn. Thank you very much for joining today from the Netherlands. Can you tell us what you do, and most important, how you could help embryonics on that manufacturing of the laser?
Yes, thank you very much. So yeah, what we are working on is hybrid integrated lasers, right? So our core expertise, let me share my slides quickly, right? So we are really a design house, and we want to help people get things done in integrated photonics. Huh? Jose already mentioned a few of the limits. So why anyhow use integrated photonics for space? I think the typical reasons we have here are size, weight, and power always, right? But I think I envision that for space, put multiple functions on one chip is very useful. To have one optical module there, and also due to using robust chip technology, so typically radiation for most of the technology, and vibration is not a problem, even for hybrid integration. So what we offer are design solutions for integrated photonic circuits, so that for example, you can easily integrate long spirals in a robust chip, right? What we are developing here also is a hybrid laser design module, so that we have a fixed design hybrid laser designed in a chip that you can integrate, for example, your transceiver, and you can also integrate multiple transceivers, and then mixed with the menu card of different integrated photonics technologies depending on what you need. Yeah? And then we would design in the hybrid laser and the other functionalities you want to have on the chip, right? Let's say a filter. And one of the questions that, for example, for you, I would have, what specifications are you looking for, right? What is high power, right? Another interesting approach, what I also think could be interesting for sensing in space, are the to go more into the mid-infrared for this, for these applications, for example, for sensors. So happy to talk to you and how our solution might fit your need in some respects, right?
Would love to follow up. So we have many different applications, so lots of different things to talk about, definitely.
David, one more thing. Whenever I bring you on a stage at any event, I always ask you the same question. So is packaging of peaks already reliable enough to survive the space?
The short answer is no, but again, depends on the form factor you're doing. There are ones that are fiber attached that I'd say would survive going to space, but there's needs for different form factors that need more work, definitely. Yeah.
David, I'm going to have fun now. Wait, John, maybe disagreeing with David, allow me to bring John Dawes from Fix. John, thank you very much for coming to the meeting. I think you have a success story to share.
Yeah, thank you very much. I think so as well. I'm not sure if you can see my screen now.
Crystal clear.
Yeah. Okay. Now, so we have been working in the past already with NASA doing a LiDAR system for landing gear, so for different missions. And they have been doing quite some extensive reliability testing on that, which they published recently with an OSA event, actually. So that's fantastic. And this is for the Picard platform. So this is a LinkedIn post. It's also very nice to showcase that today we actually bursted the 10,000 followers. So that's another happy moment for us. But also this has been tested and published. So I think that's really nice for the space applications. And we are working now with both ESA, NASA and DLR to actually validate if we can release the package itself, so the housing, independently for the integrated photonics functionality that you have inside. So that's also to make prototyping for space applications a lot easier, that you don't need to go to the full qualification each time.
David?
Really nice. Yeah, no, fantastic. Yeah, no, I will follow up. That's really encouraging here. Yeah.
Jeroen, thank you very much for joining. David, one more thing I want to, whenever I bring you on a stage, there is so many things that we need to discuss, but many people, when we talk about space, they want to look at the longer wavelengths. So we have a question in the chat from Ali Torabi from Lawrence Semiconductor. Ali, what's on your mind?
Thanks, Jose. So I posed the question about extended wavelength regimes for QKD specifically. One of the things, so just as a way of short introduction, we're a 33-year-old group for epitaxial services business in Arizona. So since '92, we've been helping other companies with their silicon germanium, pure boron, and more recently silicon-28 device structure development, epi-wafer R&D, and foundry production. So we have a fleet of 14 ASM CBD reactors and a lot of metrology characterization capabilities and material scientists. More recently, we've been both supporting other companies, but developing some of our own detector and emitter technology based on silicon germanium tin. And basically the concept is to commercialize germanium tin-based optoelectronics devices where we can extend the wavelength range of silicon out into certainly through SWIR and into the mid-wave. So we've demonstrated decent dark current detector performance out to about 3.2 microns. And the sweet spot is probably 2,000 to 3,000 nanometers, so 2 to 3 microns. And we also know there's in the literature been some early development of single photon detectors in that 2 to 2.5 micron range. And so one of the applications that we're interested in enabling with that is single photon detectors in those atmospheric transparency windows around 2.1, 2.3 microns.
I was going to suggest.
Yeah, and we're not, so this is new for us. I mean, we historically have not been a device company. We're looking for partnerships with device designers, developers, and module developers, integrators. We're pursuing both commercial and DoD funding to support the development beyond what we've done internally. But again, getting some understanding from you all who are in the field, much more experienced than we are as a business, commercializing technologies for these applications. I'd be very interested to know how attractive that would be. Would it be something really enabling for a new type of, secure communication system if we could develop scalable, affordable, single photon detector products at that 2.1 micron range?
So short answer is definitely for the ground to space links, that has a lot of interest. Anything you can do to increase the photon efficiency and also let's say in the right attenuation window is very good. It's also actually from an atmospheric distortion perspective, a bit more robust wavelengths, the adaptive optic systems become more robust. What I'd say is the challenge from a wider adoption from a networking perspective is the standards really are coalescing to sort of 1550 type communications. That's going to be the prolific link. But I would say definitely the ground to space link though is open for better technologies that can really solve those problems. So yeah, definitely it's an interesting solution.
Chris Mahoney, welcome to the meeting. Chris, you and me have been simulating live in Optica events online in front of hundreds of people space links. Can you shed some light on us? What is the right wavelength here? And also, what brings you to this meeting? How can you collaborate with Embryonics and everyone else in the room?
Yeah, thanks, Jose, for the introduction. And maybe just to address Ali's point he was just making, this is the type of thing that can be explored through simulation. So exploring these different wavelengths, how does the performance of a custom photonic integrated circuit impact the overall system performance of your free space optical communications link? This is a perfect thing for simulation. You could sweep wavelengths. You really can do whatever you want that maybe you can't do in the lab physically. And it's more efficient to explore these things this way. So, at VPI Photonics, we provide photonic design automation software. And so we have solutions that cover these different levels of abstraction. So from devices, so designing waveguides and fibers, up to components, which is more like designing a photonic integrated circuit. Maybe it's a PIC-based laser that we've been chatting about, but also physical modeling of fiber lasers and amplifiers. And then we even get into more systems level simulations for these free space optical channel links, optical inter-satellite links, uplink, downlink, but also for quantum communications as well. And so we've been part of the European quantum flagship projects over the years, and we've developed some QKD simulation capabilities around that. More recently, we provide tools for network design. So actually hybrid networks. So including laser satellite links with optical ground terminals, and then the fiber distribution systems as well. So planning those full networks. And so, a few things that, separate us from some of the other software vendors is that, first, our software is integrated. So if you're designing a PIC in the same interface, you can actually simulate how that affects your, your bit error rate of your optical communications link. It's interoperable. So if you've already done some Python, MATLAB scripting, code simulations, we can bring that into the software as well. And then in terms of just being industry leading, we're always progressing, adding new capabilities to the software. I just want to highlight one use case. This is kind of what we've been talking about for the past 30 minutes or so, is these optical satellite links. So we can simulate these in a schematic-based environment. On the left side, you see we have a transmitter. This could be NRZ, PPM, coherent transmitter. And then what we've really been working on recently is this a free space optical channel model. So it includes atmospheric turbulence, um, conditions from weather, from wind, from different elevation levels. And more recently, we've expanded this into coherent detection. And we can include coupling into your fiber. We can include a system level adaptive optics simulation as well, and see how digital signal processing, adaptive optics all impact your overall bit error rate, your constellation diagram, eye diagram, things like that. So yeah, we have solutions to uncover some of these the answers to your questions. Next week I'll be at ECOC. If anyone wants to connect, happy to connect in person. You see my email there. Yeah, so thanks for the opportunity here.
Thank you, Chris. Chris, we've heard already quite a few presentations, from youth about their mirrors, from Jorn about their solutions with the laser and with the hyper-integrated laser. Can you plug all of these solutions into your software to simulate the system that might, photonic system ground station for David that will incorporate all of them?
Great question. So I'll say yes, but really depending on what you want to do. So I'll give you an example. If you're doing some electrical optical co-simulation, co-design, maybe we don't have all of the capabilities in the software, but we do have partners. So we partner with Keysight, and so you can actually launch our software directly from Keysight ADS as well. If you're doing, let's say, the telescope design. Now, we don't really get into ray tracing, but we can export a Zmax beam file from our software. So then you can go to another software with more expertise in ray tracing and bring that back in. So we try to be the glue that can hold your photonic design workflow together by offering this interoperability. So most of this can be done in the software. If you can write it in Python or MATLAB, you can definitely add it into the schematic here as well. So we offer different solutions to bring in those other types of modeling that are necessary.
Are you also open for partners to reach out and say, I have my solution. I would like you to be able to plug it into your software?
Yeah, definitely. Feel free to reach out to me. My email's right there at the bottom of the screen. We have our own API, so it's ready to go. It's full of the documentation's complete. So if you want to plug something into our software, yeah, just reach out and we can connect.
Thank you, Chris. So then I'll suggest you smoothly move from the communication to actually observation. Because yes, beyond the communicating with, if we look at the beautiful images from the from the James Webb Telescope, these images needs to be communicated down, but first of all, they need to be recorded. And so for the observation, Earth observation, I'd like to invite to the floor our speaker who has really made a name in the designing optical systems for the Earth observation. Of course, I'm talking about Eric Rook from Zafran. Eric, are you with us? Please join the floor. The attention of everyone is yours. Eric, are you with us? Maybe we lost him. And Antonio, then I'll come to you. You posted interesting quote, optical echoes from the moon. Antonio Raspa, what did you mean with this? Oh, Eric?
Hello. Yeah.
Yes.
Sorry. Can you hear me?
Yes, we
Okay,
hear
good.
you pretty well. Please start.
Sorry for that.
No stress.
Okay, so
Now we're
can
all
you
in
see my screen?
anticipation. Not yet.
Okay.
Just a second. Yes, it's loading. I believe it will be here soon. No.
No, can you?
No. For me, maybe it's only me, support team.
No, we don't see it.
Okay,
You don't
maybe let's
see.
try again.
Yeah, we'll try again.
In the worst case, Tulsi, please prepare the slides.
Just stop.
Yes, let's try again.
Yeah.
It worked on the practice. That's how it always
Yeah,
is.
it worked always. It works on the rehearsal. It always worked. No.
No. Dulce, do you have the slides?
Yes, I do.
Please share your screen and then progress. Eric, then Tulsi will progress for you. The slides, just tell her next slide, okay?
Yeah.
Perfect. So she's loading. Just a moment. Technical glitches always happen. All right. You need to press Ctrl Lock to make it full screen. Yes. Eric, once again, welcome. Okay. And we're all all anticipation. Now you really made the room hot. Everyone is looking forward to your presentation.
Exactly. Yeah. Okay, so I will go through a few challenges which I think will encounter the companies who are working as a solution for the NewSpace. So can you move to the next slide? So what are the challenges? I think that first of all, there will be a combination of many different ways to observe the Earth, and it goes through the complete spectrum of wavelengths. It will start with the radar satellite going to a long wave infrared, the shortwave infrared, visible. They will really look at images, but it will also look at a spectrum to get more data about what we can really see from the Earth. And this will help us to better understand what's moving on the Earth, what's going on, and things like monitoring disasters, fires, as you can see on those pictures. And this will be probably a combination of many different way to observe the Earth. Can you move to the next slide? So I will more specifically speak about the imager for optical wavelengths in the visible spectrum. One of the first challenge will be to reduce the volume of the optical instrument, reduce the mass of the instrument, and to be able to decrease the total mass of the satellite, the platform, to be much more compact than what we have seen in the past. And this will mean having optics which will need to be much faster with very low F number, more and more the use of freeform optics in space. That's a new trend that has started a few years ago, but I'm convinced that this will be increasing in future optical systems to be much more compact than what we can have in current or previous system. The second challenge will be to be able to reduce both the price and the lead time of the payloads, because there will be increasingly need of constellation of satellites with numbers of images to be produced. And this will be, I think, also a challenge for the optical community to really produce fast and cheaper our systems. Can you move to the next slide? And of course, the requirement while making smarter and smaller optics and smaller systems will be to increase the resolution of the system, going from a few meters to much less than a meter, and providing a service which will give much more information to the end customer in the image that will be delivered. And of course, there is another challenge, is that the numbers of debris in the space will also increase and is increasing, and this is becoming also a real challenge for the satellites, and so be able to monitor the debris from both ground and space, and be able to define accurately what are the threats and how to deal with them. This is also becoming a very interesting subject for not Earth observation, but imaging from space to space. Can you move to the next one? So we have very recently launched at the beginning of this year systems that provide, say, a very medium resolution around the 10 meter, but with a very compact optical system. You see the total payload. The main, I'll say, most of the volume is taken by the external baffle of the system, but the optical system in itself is as small as a shoebox, and with a mass less than a few kilograms, in fact less than 10 kilograms in total. It has been produced in about 12 months, and you see some of the pictures, images that have been taken in say the Nordic regions of the northern hemisphere. So that provides the medium resolution type, be able for many type of different missions that can use this type of instrument. If you move to the next slide, it shows a system that has been designed to provide a 1 meter resolution in a system which fits in a 27U. It's a little bit heavier, but only 12 kilograms in total. So still a very lightweighted system. It's again to be produced in a 12 months range of time. And at the moment we are being able to produce about one of every month of those types of systems, and getting to 20 per year in end of 26 and the full year of 2027. So this addresses both a very compact and I think very powerful space imager, and with the capability to be produced in fairly large quantity as far as the space business is concerned. Next slide shows what's currently in design. So that's a higher say resolution system aiming at producing a native resolution of 0.5 meter with also image capability enhancement and onboard processing to improve the image resolution that can be provided. That will be fully qualified end of next year, and we're aiming at having a first flight in 2027, and the production time of about 18 months for this system, and at the beginning being able to produce about 4 to 6 of those instruments every year. So that's our range of seeing instrument addressing those type of challenges, always trying to make it more compact, lighter, and be able to be produced in a reasonably time frame. I think that's all. The last slide is just a summary of those family. There was a one on the bottom right that I didn't mention. That's the seeing the TACT, which is used for the space situation awareness from space to space, which is currently being manufactured and will be delivered early next year, and we'll have the first flight also in 2026. So thanks for your attention.
Thank you, Eric. And as we ask all of our system integrators, what are your top 3 challenges that you would like to postulate to this community to hopefully being addressed by them?
Yeah, I think that the first real challenge is that we need to move to or try to move to a product approach rather than a case-by-case demand with the customer coming with their own specification and need to develop, to adapt the current system to the needs. So the way to make system more affordable and produced in a shorter time is to try to standardize most of the parts of the system and only do some really small modification for a case-by-case mission. That's, I think, a real challenge for all the community to think in that way, more product-oriented in the optical instrument rather than going on a case-by-case basis mission approach.
How about the sensors? Because when you develop such a sophisticated optical systems, of course, it has to match the sensor. Otherwise, all your efforts are gone. How is the progress on this in this area?
I think there's a lot of progress in that area. There are numbers of sensors now available for different type of missions. Most of them have already flight heritage, so they have proven to be operating in space with very, very good results. And I think also that's of course moving also to standardization. And no one I think in the NewSpace community now wants really to develop a specific and new type of detector for their instrument. And they are looking at what already has space heritage, what is the best combination between this detector and the electronic, which comes with the detector, and the optical instrument. So we are fairly, so we have a lot of connection with vendor for detectors and focal plane, also electronics, and yeah, that's moving well.
I would like to bring you another connection in this field, and it's Bavo Delaware from IMEC. Bavo, you also actually have a question to Eric, so please ask your question and also tell us how you are able to address his challenges.
Yes, Eric, I had a question. So you showed the different payloads and you, shared the spatial resolution of the different payloads, and it's really nice and amazing how high resolution the payloads, especially the last one, that you can reach. I was wondering, you have not mentioned anything about SWOT of the payload. So how wide can the different payloads see, and what is actually the size of the pixel array of the detector that you're using?
Yeah, they are different from between all those different imager. For the first one I've shown, it goes to a swath of 60 kilometer. So that's a wide, what we call the wide field of view. For the medium one, the 230, we are a little bit more than 10 kilometer swath. And for the high resolution, we are aiming at 8 kilometers well. And the pixel size, again, it depending on which one of the instrument you consider, but it's typically the central difference, and we have pixels going from 3 to 5 micron, depending on the choice of the detector.
Thank you.
Bavo, is it something that you're able to do? So maybe show what you're capable of.
So switching to the next presentation then?
Yes.
Okay. I'll share my screen. Do you see my screen?
Yes.
All right. Good evening, everybody. My name is Bavo Delure. I'm working at IMEC. IMEC is a very amazing place in Belgium. It's a spin-off of the Catholic University of Leuven. In the meantime, we are 6,000 people here and working on various challenges in nanoelectronics and digital technology. And today I'm going to talk about on-chip spectral imaging for space applications, a technology that we are already working for quite some time. But since our latest upgrades on deposition tools, we have again pushed the boundaries of what we could do with spectral imaging. So from our side, we're working on chip spectral imaging, and we have a very special approach in the sense that we are not using external spectral units, but we really create optical filters that we directly deposit onto the image sensor wafer. So we have a very state-of-the-art facility within IMEC where we are exploiting basically the semiconductor tools that we have in-house to be able to really pattern very small structures in our fab. And this in combination with the optical filter deposition that we can now also do in a semiconductor environment, we can really make amazing optical structures that from a space perspective we're using for Earth observation constellations and also for planetary exploration. Unique approach of our technology is that we really have the capability to create the thin film layers directly onto the image sensor wafer. As you see on the left side, this is an image sensor wafer. This is done with our optical deposition tool, and that in combination with the patterning capabilities that we have allows us to make really small structures. What you see here are structures at the same size of a pixel. So basically, we are able to create per pixel filters in various types. Originally, we started off with Fabry Pro filters. So those are mirror-based filters that we make for our hyperspectral instruments. But in the meantime, we have expanded the portfolio of filters that we can manufacture. Since we can create very small structures, we also have a large degree of freedom in the geometry of the filter that we can make. We can organize filters in the lines, we can organize filters in mosaics, but we can also make combinations of those two. And basically the geometry of the filter is the degree of freedom that we have and can do very nice things. One example here is the mosaic detector that is flying on board of the Hera mission of ESA. The other device that I wanted to show is the latest device that we created on our new deposition tool. And this is a 96 band hyperspectral imager covering the range 450 to 900 meters inside this 2 megapixel detector. On the CMOS devices, we are doing the filter deposition directly onto the image sensor wafer. However, we also have already quite some heritage on shortwave infrared imagers. And this is, for instance, a copy of the Sentinel-2 band setting that we created for a small satellite mission. So this is developed for an in-gas detector. In the meantime, we also manufacture filters for MCT detectors, so to expand actually the wavelength range from 400 going up to 2.5 micrometers now. So this is in short our latest developments that we are having. So there are, for the moment, more than 30 devices in space operated in constellations, and yet a whole bunch are being launched in the coming weeks.
Thank you very much, Babo. Thank you very much for being with us today. Thank you also, Eric from Safran, for being one of our best integrators of technology. Many people are demanding to be in touch with you. It is 5:30 p.m. It was a great meeting, actually. I'm really happy with all of you. It is 5:30 p.m. What I'm going to do now is I am going to close the meeting for the live stream, and then I will make sure that all of you who want to stay afterwards, they can stay for an after event drink. But now let's close the meeting for the live stream.